All right, we're talking about oxidation numbers and calculating oxidation numbers, particularly in compounds and in ions. What we're really left with is several rules that we can use to determine the oxidation numbers. And so if I go back, elements have an oxidation number of 0. The monatomic ions, their oxidation state is their charge. Metals are positive, nonmetals are negative most of the time. Oxygen is the one that you can assign with confidence as a -2, except if it's in a peroxide. You don't see that too often. Hydrogen, when bound to a metal, is a -1. You don't see that often. What you see most often is hydrogen bound to a nonmetal, which is a +1. And the halogens, you begin to, and I think the best way to do this is to assume that they have a -1 charge. Most often that will happen unless you have more than one halogen bound together. It is safe to say that it has a -1 charge. The sum of all the oxidation numbers in a neutral compound is 0. The sum of the oxidation numbers in a polyatomic ion is a charge. And I have no idea what this means. I would say there's one oxidation number for each element. Okay, and so we did the first 3. Sulfur at the top in A has a -2 charge. Based upon the rules, the hydrogen is a +1. Sulfur 8 is the elemental form. It has a 0. The sulfur dichloride, in this, the one that I know is the halogen, which is -1. I had 2 of those, so I have a -2 charge for the chlorides. So the sulfur must be a +2 because when I add up all the numbers, I should be 0. All right. You can see that the oxidation number for sulfur has changed. In this, the oxidation number for oxygen is a -2. The alkali metals are always a +1. So on this side I have a +2. On this side I have a -6. And it all has to add up to 0. What must sulfur be for that to add up to be 0? A plus what? 4. So sulfur in this case is a +4. In this last case, when everything adds up, it has to be a -2. Oxygens are a -2, so I have a -8 total here for oxygen. What must sulfur be for this to add to a total of a -2? Pull out your calculators. There's a total of a -8 charge for the oxygen because each oxygen has -2. And when you add up to become a when you add up whatever sulfur is, it has to end up as a -2, so it has to be a plus what? +6. So in this first case, sulfur was a -2. In this case, sulfur was a 0. In this case, sulfur was a +2. In this case, sulfur was a +4. And in this case, sulfur is a +6. Based upon how the reaction has occurred and what the compound that you're given. All right? And so we know halogens, -1. We know alkali and alkaline earth metals, +1, +2. That's good. Oxygen, -2. That's good. Based upon those that we can assign, that we know, then there's usually one that we have to calculate, and they're usually in the middle of the nonmetals, and they can have various charges based upon, or oxidation numbers based upon how the molecules put together. So that's important to be able to calculate those. Because in the next step, we're going to actually be using oxidation numbers to justify what's going on. Remember oxidation reduction, the simple definitions. Oxidation, I lose electrons. If you lose negative, you become positive. Reduction, the gain of electrons. I add negative charges, the overall becomes more negative. You can remember this by Leo-Gur or oil rig. Leo-Gur is loss of electrons is oxidation. Gain of electrons is reduction. Okay? Or oxidation is loss, reduction is gain. Okay, so that's just a little mnemonic to help you remember what oxidation and what reduction is. Now, this is how I kind of look at it. All right, here is a redox reaction. Okay, and in this case, something's going to happen, and so I go from zinc to zinc. In this case, the zinc's oxidation number is 0. In this case, in the product, what is the oxidation number of zinc? +2. So, down here, I have two other things, oxygen to oxygen. In the beginning case, this is 0. In the ending case, oxygen is a what? -2. Oxygen has gone from 0 to -2. I had to add 2 electrons to get there. In the top case, from zinc 0 to +2, I had to lose 2 electrons. Okay, and so zinc is oxidized, oxygen is reduced. Zinc is oxidized, oxygen is reduced. Okay, and so we have to track where the electrons have gone. Remember, redox, reduction, oxidation. If something is oxidized, something has to be reduced. So you have to identify which two players are happening. All right. In this case, if we take a look at this, oxidation of metals by an acid or a salt, in this case it's going to be an acid. Zinc goes from here to here, okay? And hydrogen goes from here to here. In this case, the oxidation state of zinc element is 0. The oxidation state of hydrogen in the acid is a +1. In the final case, zinc is a +2, and hydrogen in the elemental form is a 0. And so, zinc again has to lose 2 electrons, okay, to get to that point. I'm going to gain 1 electron times 2 to equal a total of 2 electrons. I add 2 electrons in this case. There are 2 protons. Each one will gain an electron to become H2. And I have 2 at the top, 2 at the bottom. The electrons have to be even, or have to, if 2 move, we have to make sure that they're balanced. All right. So zinc is reduced. Zinc is oxidized. The hydrogen is reduced. Something else is called an agent. An oxidizing agent is reduced and causes something to be oxidized. So zinc is the item that is reduced and is the oxidizing agent. No, is that true? No, zinc is the one that is oxidized, okay, because it lost electrons, and so it is the reducing agent. Hydrogen gains electrons, so it is reduced, and it is the oxidizing agent. I hate when they use these terms, but you will see agent referred to in some books, and it seems reverse. All right. So in this case, what's happening? The 2 things that are changing oxidation states. These are the 2 things. What is the charge of iron in the reactant? 0. What is the charge of nickel in this case? +2. Because you see that there's a 2 here, it must have been up there, and it's +2. What about the iron here? +2. What about the nickel? 0, because it's the elemental form. So zinc had to lose 2 electrons. Nickel had to gain 2 electrons. If I lose, oxidation. If I gain, reduction. So nickel is reduced, iron is oxidized. All right? Now, I could give you a whole equation like this and ask you which one's oxidized, which one's reduced. If iron is being oxidized, it is the reducing agent. And if nickel is reduced, it's the oxidizing agent. And so you can label them. So if I give you the entire equation, you can identify these pieces. But I'm not just going to do that. I'm going to ask you to predict if these reactions will actually occur. And what we're going to look at is something called the activity series. Now, I will never make you memorize the activity series, but I will ask you to use the activity series. And what happens is, what we're trying to do is let you know how reactive is a metal. But you need to know how to read this, okay? You're going to be comparing 2 metals to see if they react together, okay? That's the big deal. Here's the clue. The lowest one wins, okay? The lowest one can steal electrons. Okay, so how to read this? When you read this, let me go back and do a different color. If the charged ion is below a metal, okay, what this says is copper wants 2 electrons. Zinc has all of its electrons, okay? And so copper is looking for electrons, wants to take them. If by chance copper is lower in the list, it is reactive enough to steal the electrons away from zinc, okay? If by chance iron 2 attempts to react with silver, iron 2 wants to steal electrons. But silver holds onto its electrons stronger. The iron will not take the electrons from silver. The iron 2+ doesn't take the electrons from silver. So this right here is no reaction. But this will actually cause a reaction. The copper 2+ is reactive enough to steal the electrons from zinc. Okay? So we're going to refer to this table to see if a reaction will occur or will not occur. And so if you take a look at this, copper and silver, silver plus, I'm going to go back to that. We said we have silver plus and we have copper. Will silver plus take away copper's electrons? Silver plus is below copper. What's really going to happen is there is a piece of copper metal. That's the elemental form. This is a solution of silver ions. If you actually take a look at this, look what happens to that copper. It becomes a little bit, it looks fuzzy. Here it looks even more fuzzy. And then what is the color of the solution? Can you see it a little bit in that last picture? You see the solution here is clear. Can you see color in the solution in the end? Slightly what? Green or bluish. Okay, what has happened is the silver ions are floating around, but when they get to that copper, what's going to happen is it's going to react with the copper and it's going to deposit silver metal because the elemental form will be formed, and the copper ion will float around, and copper has a color associated with it. And so you see the copper being solubilized or dissolved because the copper's electrons are being taken away by silver. And this growth here is the silver coming out of solution. The reaction in reverse doesn't occur because a copper 2+ is too weak to take its electrons away from silver. So, here's a question. Write a balanced molecular and net ionic equation for the reaction of aluminum with hydrobromic acid. Okay? Well, before we do anything, we've got to look at the list. Hydrobromic acid. What is the cation of hydrobromic acid? What would it be? What is the cation of hydrobromic acid? H+. All right, and it wanted us to react it with aluminum. Is the cation below the metal? Yes, the reaction will occur. Okay, so that complicates it. That actually makes us do a reaction. So aluminum plus hydrobromic acid will yield, okay, aluminum will react and give up all of the electrons it can. How many electrons does aluminum like to give up? What charge does it become? A +3. All right. What is the anion that is in this solution? Br. Yeah, I answered my question before, which is a -1 charge. So what we're going to do is we're going to make AlBr3 plus elemental hydrogen, which is H2. Is this balanced? No. All right, we got a problem. I could put 3 here to balance the bromines, okay? If I put a 3 here, I'm going to have 3 hydrogens. But hydrogens can only go up by even numbers. So I could put a 3 here, but that doesn't work.
6.
Yeah, the next one, I could put a 4, that's not going to work. I could put a 5, that's not going to work. But a 6 would be the least common denominator. And if I have 6 bromines here, then I have to make 6 bromines there. And now I have 6 hydrogens. I can get 3 there. Okay. And now the last thing I have to balance is what? Aluminum with 2. Now I saw that. You may not see that. You might have had to try 1 there. Does that work? No. 2 there. Does that work there? No. 3 there. Does that work there? No. 4 there. Does that work? 5 there. 6 there. You would eventually get to it. Okay? But you probably would have started with at least 3 and then found out that that doesn't work. Okay? All right. To do a net ionic equation, this is solid. This is aqueous. Bromides. All bromides are soluble except for what 3 things bound to it? Silver, mercury, or lead. This is aqueous. And this is a gas. Does aluminum break apart the solid? Nope, drop it down. Is hydrobromic acid a strong acid? Yes or no? Yes. How did you know that? Because there are 7 of them. This is one of those. If it is a strong acid, they ionize completely. 4 things that I have to do. What is the ion? It is hydrogen. That's the first thing. What is its charge? +1. That's the second thing. How many do I have of them? It's the third thing. How many?
6.
And then label it. That's the fourth. What is the next ion? Bromine or bromide. What is its charge? -1. How many do I have of them? 6 of them. Label it. Does aluminum bromide dissociate? It is aqueous and it is an ionic compound, so it dissociates. What is the cation? Aluminum. What charge? 3 plus. How many do I have of them? 2, and label it. What is the ion? The anion? Bromide. How many what charge do I have? -1. How many do I have of them? Be careful. 6. Label it. What is hydrogen? Does it break apart? No. All right, what are the spectator ions, if there are any? Bromine. 6 of those, 6 of those. The ultimate equation is for the net ionic, 2 aluminums plus 6 protons yields 2 aluminum, 3 pluses plus 3 hydrogens, gases. So that is what's floating around in the solution actually doing the reaction. Okay? The additional step, you learned how to balance an equation to predict products. That was something I assumed you were able to do. You were, so predict products and balance it. I assume that. Labeling them, whether they are solid, liquids, gases, or aqueous. That's something that I assumed you knew. Being able to break them apart and dissociate them correctly. Already, I knew that you should be able to do. The key to this one was, did the actual reaction happen? Using the activity series, we justified that yes, the reaction will happen. Yes, this single displacement type of reaction will occur, and you can go. If it didn't, we would just write NR and we would have been done. NR means what? No reaction. Okay? Will an aqueous solution of iron 2 chloride oxidize magnesium metal? That's another way of saying, does it react with magnesium metal? If so, write the balanced molecular equation, net ionic equation for this reaction. Okay, so the two things that are reactant, iron 2 plus and magnesium. All right, iron 2 plus is right here. Where's magnesium? Right there. Unfortunately, does this react? Yes, that means we actually have to do something. Okay. So, iron 2 chloride, Fe, Fe 2 plus, chloride is a 1 minus, so the compound looks like this. All right. All chlorides are soluble except for chlorides that have, what, 3 metals? Silver, mercury, or lead. So this is aqueous. Plus magnesium, metal. That's a solid. Yields. Okay. What? Well, I'm going to singly displace. When magnesium reacts, what charge does it become? Plus what? Plus 2. Chloride becomes -1. Magnesium chloride plus the iron will take up enough electrons to become neutral and become its element. And all chlorides are soluble except for silver, mercury, and lead, so this is aqueous. Is this balanced? Oh, it is. Don't make it any harder than it is. Don't try to balance it. Don't try to mess up a balanced equation. If it's balanced, it's balanced. Does the first compound dissociate? Yes. The cation is iron. Its charge is +2. It has 1 of them, and then I label it. Plus, the ion is chloride. It has a -1 charge. The 2 is there. I did not drop down Cl2. Cl2 is the elemental gas. Okay? That's not what we had. We had -1 chloride ions. and it's aqueous. Plus, does the solid break apart? Nope. Drop it down. Yields. Does magnesium chloride dissociate? Yep. The cation is magnesium 2 plus one of them aqueous, plus the anion is chloride 1 minus 2 of them aqueous, plus iron solid. Spectator ions are chlorine itself. Anything else? Nope. So the reaction is Fe 2 plus magnesium solid, that was aqueous, yields magnesium 2 plus iron, that's a solid. Iron and magnesium. Is iron oxidized or reduced? It is reduced because it has to gain electrons. Is magnesium oxidized or reduced? Well, that's good. You know, if one has to be oxidized, the other has to be reduced. It is oxidized because it loses 2 electrons, becomes more positive. The top one is not always oxidized, the bottom one is not always reduced. If you saw my examples, that's what happened. You just can't memorize it that way. You actually have to see what charges things are becoming. Okay. Will lead and mercury, mercury 2 nitrate actually react together to form this compound? Okay, in this case, I would have to go back and look at the chart, and I don't have the chart easily accessible. Actually, let's see, where's the chart? In this case, mercury is way down here. Mercury is here, and lead was what we were reacting with. Where's lead? Lead is right here. Mercury, the ion is lower than lead, so that reaction will actually occur. In this case, chromium and aluminum. Will that actually react? Chromium 3 plus. Where's chromium? Chromium 3 plus. And what was it? Aluminum? Yes, chromium 3 plus is below the aluminum. So that's cool. So that will react. We could predict the products. Lead and silver. Lead 2 plus and silver. Okay, I'm going to go forward. Actually has no reaction because lead 2 plus being right here and silver being right there, no reaction occurs. Stop. So we would write no reaction for that one. This last one, iron plus nitric acid yields iron 2 nitrate and hydrogen. Does that actually react? Iron 2 is right here. No, sorry, it wasn't iron 2. It was the acid plus iron. The acid is lower than iron, so that reaction will occur. The H plus will react with the iron, steal its electrons to create H2, the element, and the iron will become charged and it will become a +2. And so we could ask you to say, does it react or doesn't react? You will be reading the activity chart. You will not have to memorize that. That's way too much. All right. And so if we look at a couple reactions, these are net ionic equations or full molecular equations. How will we classify these? Okay. Are they metathesis, precipitation, Are they neutralization? Are they redox? Okay. And so ultimately what we see, the first, when I actually get to lead 2 plus, aqueous plus sulfate minus 2, aqueous gives lead 2 sulfate. What kind of reaction is that? It's a what? It is two things we can label it as. It came from a metathesis reaction, but the particular type of metathesis reaction is a precipitation. We formed a solid at the end, which is precipitation. Silver plus 1, iodide minus 1 makes silver iodide. Okay? In both cases, silver is plus 1. In both cases, iodine is minus 1. And so it came from a reaction that was a metathesis, but because it formed a solid, it is also a, more correctly, precipitation metathesis reaction. All right, this next one could be a little bit confusing. All right, we have calcium, copper 2 hydroxide, and the proton is copper 2 plus water. In this case, your choices are metathesis, precipitation, neutralization, and oxidation reduction. All right. In this case, there is no precipitation because you didn't form a solid, so it's not that. Copper starts as a plus 2, ends as a plus 2. Hydrogen is a plus 1, and in the end is a plus 1, so it's not redox. I do swap ions, but in this case, it is an acid plus a hydroxide, an acid plus a base. It is a special metathesis reaction called a neutralization. If you say it's a metathesis reaction, that's only partially correct. It is more, it's better described as a neutralization. It's a very special type of metathesis. Looking at iron 2 oxide, iron 3 oxide plus carbon monoxide yields iron plus 3 carbon dioxides. Okay, what you see is, okay, iron, here it is a 3, here it's a 3 plus, here it's a 0. Okay, that's not just a metathesis reaction. In this, I can calculate the oxidation state of oxygen is a minus 2. Here, carbon has to be a plus 2. Here, oxygen is a minus 2. I have a total of 2 of them minus 4, so here it's a plus 4. So I go from a plus 2 to a plus 4. And so what you can see is one of them gained electrons. One of them lost electrons. The one that gains electrons is reduced. The one that loses electrons is oxidized. So this is a redox. What do you think the bottom one is? What can you see very, very simply about the zinc? It goes from what oxidation state to what oxidation state? 0 to plus 2. All right. One of the things are going to be oxidized or reduced. That means there has to be, if one is, in this case, going from 0 to a plus 2, it loses electrons. Okay, that must be oxidized. There's something else that must be reduced. So that is a redox reaction also. All right. So identifying what kind of reaction that we have is one step further to, we can make you do a net ionic equation, but this is trying to think backwards once you get to the final step, what actually occurred. Okay. The last concept, and you actually had a lab about this. I wish they had taught you the concepts behind this when you actually did the lab, but here it is. Okay, we're going to express concentration. All right. Up to this point in time, okay, until this chapter, we talked about a compound, and we talked about it could be a solid, liquid, or a gas itself, okay, and the solution, or we haven't actually talked about solutions, we just talked about the element being a liquid. It could possibly be a liquid. But when we go into the chemistry lab, almost always we do reactions inside a solution in which the compound is dissolved in water. That's why we had to talk about net ionic equations, because we place these compounds into water, mix them all together, and reactions occur that way. So we have to understand what happens when things are in water. What we haven't done at this moment in time in the lecture is talked about concentration. How much is in the water? Okay, and so we'll talk about that. Very simply, we're going to introduce one new conversion factor, and that's the term molarity. Molarity is expressed as a big M. Okay, that is moles of material or solute divided by volume of the entire solution. Okay, and that is in liters. And so we can write big M next to a number, but that means that I can automatically put moles, liters, and substitute that unit. Almost every time you see a number that has a number on top and a number on bottom, that becomes a conversion factor. And so I can convert a solution, okay, into number of moles and to volume by doing this. Now, here's a big deal about how you think about things. And this is where the map is supposed to help you, but most people tell me it confuses them. Okay? Grams. What is grams? A term of what? Mass. Okay, mass. You can have grams of material, right? And you can always convert grams of material into moles. So grams of something A into moles of something A. What is the conversion factor that you use to do that conversion? Molar mass, which is grams for every mole. Okay? So that conversion, we know. There's a molar mass calculator, or you add up the weights of every one of the elements to find that out. All right? We also convert the grams of A into a volume of A. Okay? Most of the time, in terms of solids and liquids, we use the conversion factor called density in terms of grams per milliliter. For solids and liquids, for gases, we use a term of gram per liter. So there are two densities, but we can change the grams of A into a volume of A, but that is a pure volume of that particular compound, okay? Could be solid, could be liquid, or could be gas. We've taught you that. We also taught you this last chapter. We can go from moles of A to moles of B, okay? There, you need a conversion factor called the molar ratio, and I can get the molar ratio from two places. What are the two places I can get a molar ratio? Equation, not just an equation, a balanced equation. Okay, and so if 2 hydrogens plus 2 oxygens yields 46 somethings, you can get the numerical numbers from the balanced equation. Okay. The other thing that we learned from a compound, okay, and so let's say if I have aluminum oxide For every 2 aluminums, there are 3 oxygens. That's another place I can get a molar ratio. It's from a balanced equation or a molar ratio. And I can change from one thing to another. Okay. We have now just introduced to you one more term. We can get into solutions. So the amount of A dissolved in some volume of water or some volume of a solvent. And so I get to solution, and I will get into the concentration, okay? And I can get a volume of liters for a solution. And what I'm going to use here is molarity. These are the big conversions that you can do. You can go from volume of A itself to grams of A itself, grams of A itself to moles of A itself. We can go from moles of A something to moles of B something. Or we get to the volume in liters of A in a solution, meaning that A is dissolved in something and it's going to be a solution. These are the big key conversions. Now, volume. If I get you up here in volume and I get you milliliters, I can change milliliters into anything I want. I can do cubic inches because you can change milliliters into centimeters cubed and centimeters cubed into inches cubed. Any volume I can interconvert within in that. Okay, and we've asked you to do stupid problems like that. Okay, and if I get you into grams, I can make you convert it to femtograms because we can convert grams into any types of grams. Okay, and I can, moles are pretty simple, moles. Moles can be converted one more big piece. There's one more thing that we can get into, numbers of things, and that's using Avogadro's number. Okay, so moles convert into moles of something else. But here I can get milliliters or liters of solution, and I can actually make you do milliliters of solution, all sorts of things in solution. But these are the big key things in which we can convert. Now what the chart does for you is say, okay, moles of A, you have all of these conversions, and if you get to moles of B, then you can go to their volume of solution, and you can go to their weights, and then you can go up to their volumes, and the map just gets bigger. But the key thing, a density, is a conversion factor that gets from one key area to the next. Molar mass goes from one key area to the next. Molar ratio goes from one key area to the next. Avogadro's number goes from mole to numbers of things. And molarity is the last piece that we're teaching you to make big types of conversions. The reason why we use molarity is that is how things are used in lab most often. Now, when you take a look at molarity, okay, molarity is associated to everything that gets dissolved. And so potassium nitrate, all nitrates are soluble except for nothing, so all nitrates are soluble. When it actually dissolves in water, it becomes aqueous, and you've got 2 dissociated ions. So if you dissolve up 1 molar solution of potassium nitrate, what really is floating around is 1 molar solution of potassium plus 1 and 1 molar solution of nitrate minus 1, all floating around. If you take a look at sodium sulfate, it will dissociate into 2 ions. But if you put in 1/2 a molar sodium sulfate, what you get is broken into 3 pieces. You will get 1/2 a molar of sodium plus 1/2 a molar of sodium plus 1/2 a molar of sulfate 2 minus. You can rewrite that and say you have 1 mole of sodium floating around and 1/2 a mole of sulfate because it dissociates into 2 or twice as much sodium. Okay? And so this is important an important concept. It will turn into a question on the exam about how these will dissociate and how many moles of things are roaming around. So, simple calculations for molarity. Okay, it can be as simple as this. You have 23.4 grams of sodium sulfate dissolved in enough water to form 125 milliliters of solution. Okay? And to do anything, all we're going to do is conversions. Now, we're going to set this up. Molarity has an amount on top and a volume on bottom. Now, the amount needs to be moles, and the volume needs to be liters. We are given an amount and a volume. We're given 23.4 grams of sodium sulfate in 125 milliliters of solution. Okay? I have the amount on the top and the volume at the bottom, but I do not have the correct units. So, what do you want to change first? You're going to have to change both grams and milliliters. What do you want to do first? Does it matter? No. I've got to get the bottom to liters and the top to moles. So what multiplication do you want to do first? Let's change what to what? Milliliters to liters? Okay, great. If I have 1 milliliter, it's 1 e to the what? -3. Oh my goodness, that's like way back to chapter 1. Okay. I now have grams per liter. That is a concentration, but it's not the concentration I'm looking for. I'm looking for molarity. So how do I change grams to moles? I use the molar mass. And lo and behold, we gave that to you. Grams of sodium sulfate into moles of sodium sulfate. 1 is 142.00. And I can either write as the unit, okay, M sodium sulfate, or I can write moles per liter of sodium sulfate, because those are interchangeable. Okay, so a piece of the puzzle is for you not to be confused about big M being exactly the same as moles over liters. All right. Unfortunately, you will learn this in GChem 2. It must be a big M, because a small m stands for a different concentration, a different type of concentration. So capitalization is important for that. And so 23.4 divided by 125 divided by 1 e to the -3 divided by 142 will give you the concentration in molarity. Okay? And so we can solve something that simple. But molarity calculations can be one of two types, just a conversion. This one is a conversion. Okay? This one is also going to be a conversion. Okay? With a known molarity, you can calculate the number of moles of solute in a given volume. Okay? We're just going to express it. We're going to use molarity as a conversion factor. So if I take a look at this, I have two numbers. I have this, and I have this. Which number is the conversion factor? The which one? The molarity. So 0.35 liters of this compound. Okay? And I have this, but remember I can write moles per liter. And so in every 1 liter, there are 0.500 moles of this material. Okay? Do I want moles? Is that what the question asked for? No. But can you change moles to grams? 1 mole of sodium sulfate is so many grams of sodium sulfate, and we learned that was 142.00 in our last problem. Moles now are canceled out, liters are canceled out, I am left with grams. Molarity can be used as a conversion factor. That is a lot of times how we're going to use molarity. It's just going to be a conversion factor. Okay? We will then learn one other way we're going to use molarity, and that's in dilutions, of which you actually did in lab. So we're just going to teach you what you did in lab so that you understood what you did in lab before. Okay?